Good morning, MCV for you. I am sorry to be away this morning. We are on our last unit of calculus, which has got to feel good. Today we are tying in some of our functions from last semester, last year, with our calculus skills. Today's focus is on increasing and decreasing functions, and the unit is on curve sketching. So today we're going to talk about decreasing, which is as x progresses, then y values get less. And increasing functions, if as x goes onwards, then your y values get greater. So let's look at one that we're really familiar with. If we have y equals x squared, we're going to complete this chart and we're going to sketch them. For our function y equals x squared, we know very well that the derivative is 2x. So we're just going to fill out this table of values. 410149. For our derivative, however, we have negative 6, negative 4, negative 1, 0, negative 1, positive 1, 2, and 6. Let's have a look at the graph for a moment. Y equals x squared. 4. Okay, you can draw it smoother than I can on a smart board. There we are. There we are. We know as our values go from -3 to 0 that this function is decreasing. We know as we progress from 0 onwards that our function is increasing. So let's go back to our chart for a moment. From -3 to 0, our function is decreasing. And when we go past to the right, our function is increasing. And at 0, it is neither decreasing nor increasing. It has a horizontal slope at that point. We call 0 a turning point. And that occurs when the derivative is equal to 0. If you could take a moment to put into your notes, sorry, this would not work for me, but it's page 169, has a really good summary of what we're looking at today. We're going to work on two examples. The first one, f at x equals x cubed minus 4x squared plus x plus 1. We want to talk about critical points and where this function is increasing and decreasing. We can use the derivative to tell us where it's increasing and decreasing. So the derivative would be f at x equals 3x squared minus 8x plus 1. So the graph that I'm going to do is actually a graph of the derivative. I am going to let my derivative equal 0 to find its roots so I can graph it. Okay. So that's why I'm doing it. So my derivative is equal to 0. And that happens, I'm going to use the quadratic formula, when x is equal to 8 plus or minus the square root of b squared minus 4ac, I hope you remember that, over 2a. So my x-intercepts would be approximately equal to, you may want to check on your calculator, positive 2.6 or decimal 13. So I use the quadratic formula. And the whole reason I'm doing that is just to graph it. Okay, the graph of the derivative has x-intercepts at 0.13 and about 2.6. It is a quadratic with a positive And I don't care of all the other particular points. I just know that it's a quadratic that looks like that. So I know this derivative function tells me about my original function. It tells me where there is increasing going on, where that function is positive. I know where there are turning points. And I know where it is decreasing. Let's use that. We're going to set up a table of values, and it's going to seem onerous, but it's going to be helpful. So let's look at x. Let's look at the derivative, and let's look at what that tells us about the original function. Okay, so here's my important places. Where x is less than 0.13, where x is exactly equal to 0.13, between 0.13 and 2.6, exactly 2.6, and greater than 2.6. You have to kind of budget your paper there. Trying to see my graph at the same time for the derivative less than 0.13. So this section here, my derivative is positive. At 0.13, the derivative is 0. It is negative in between 0, and it's positive again on the right side. That tells me about my original function. If the derivative is positive, my original function is increasing. There is a turning point at 0, decreasing, turning point again, and increasing. This is helpful information when I am graphing a curve. I know that my original function is cubic. I know that the y-intercept is 1. And I'm going to come up with some points as well, just to get myself anchored. I'm going to do one that's to the left of the critical points. I'm going to do one that's in between. I'm going to do one that's to the right. And I'm going to do the points that are the critical points themselves, 0.13, and the function at exactly 2.6. There's not a magic number, but 4 or 5 key points can be helpful anchors. So I'm getting some points. I am looking at my increase and decrease, and both of those things will help me draw a graph. Okay, with our calculators, let's type those in. This is what I get. Okay. For a cubic, you could sometimes use the factor theorem to find x-intercepts, but it's not particularly helpful for this one. So from the information that we have, we're going to draw. Understanding that this is going to be a rough drawing. The smartboard doesn't like it when I try and make it do too many things at once. All right. Okay, you have it in front of you. I can't flip between the two, apparently. So our y, straight as an arrow, x-axis. So from the information that we have, we are going to draw a graph. We know that we have a y-intercept of 1. We know we have a turning point at 0.13 and at 2.6. So I'm going to spread this so I can see it. I know that I have a negative value of negative 5.84. So really this scale is wonky. Okay, we'll just pretend it's right. Here we go. Y-intercept of 1, turning point at 0.13, and it is 1.06, so not a lot higher, but there is a turning point. We have 1, 1 as well. 2.6 is a turning point, and its value was minus 5.84, so wrote right there. We know to the left of the first turning point, and it looks obvious now, but it is increasing. So my curve does that. I know on the other side of the turning point, it is decreasing. And I have another turning point at 2.6, and from there it is increasing. So that, very roughly, is what our curve looks like by looking at turning points, increasing and decreasing, and some key points. Okay, our second example is f at x equals x ln x. We are going to look at our derivative to find critical points increasing and decreasing. So my derivative would be the derivative of the first times the second plus the first derivative of the second. I'm going to tidy that up. It's ln x plus 1. Just to get this derivative function drawn, I know what a basic ln x function looks like, and I know that that is a vertical shift translation up 1. We can set the derivative equal to 0, 2. If you want to see an x-intercept, 0 equals 1 plus ln x. When is ln x equal to negative 1? We would e both sides. So x is e to the minus 1, which is approximately 0.36. So I have an x-intercept of about 0.36. I know my ln function. We'll do that. So that is my derivative. My derivative tells me about my original function. That's a key point. That's where the derivative is 0. So my original function will be decreasing here because the derivative is negative, and increasing here, and this is a critical point here. So let's set up a table of values. X, we're going to look at the derivative, and therefore help us with the original function. So my key point is 0.36. I want to look at 3.36, and then where it's greater than 0.36. At 0.36, my derivative is 0. For values larger than 0.36, my derivative is positive. For less than 0.36, my derivative is negative. That tells me about my original function. It is decreasing here. There's a turning point here. And it is increasing here. Notice that my derivative only makes sense for values greater than 0. That would also hold true with the original function. This would have to have values greater than 0. Okay, we've had a look at our increasing and decreasing and those special points. Let's look at a few key points that will help us get our graph anchored. So looking specifically at the function at 0.36, and probably one on the left of it and one on the right of it. I'm choosing 0.2 and, whoops, and 2. It's up to you. Just some good points to get yourself anchored. At 0.2, my value is negative 0.32 of my original function. At the value of 2, I have 1.4. The function at the value 0.36 is approximately negative 0.368. I'm just using my calculator for these. Other really important points to look for would be the y-intercept or the x-intercept. We know that there is no y-intercept because x has to be greater than 0, so there isn't one. For the x-intercept, we are going to set our original function equal to 0 and see if we've got a nice x-intercept. So 0 equals x ln x. In this case, either x equals 0 or ln x equals 0, and that is never true. Or sorry, I'm lying to you. In that case, x equals 1. We already stated, though, that x has to be greater than 0, so that one's out. So I have an x-intercept of 1, 0. So those 4 points will help me get anchored. I've got my points, I've got my turning points, and I'm going to graph. So to create a graph of the original function, we put on our key points. So there is no y-intercept. There is an x-intercept at 1. We have a turning point at 0.36, and it is negative about right there. There is no value there. It is open, and it is decreasing from there to there. And then the function is increasing from there. It can be a very helpful exercise to check these on the graphing calculators and to use the calculators while you're working on some assignments. So calculator is a good idea. Page 169. Numbers 1 for BDF.